So let's get started. What I want to begin with is the issue of standard fluid system which you see every day. So today, after all the 3 days essentially of doing formal, more or less formal things, we'll try to make use of the formal things to talk about things which you have a feel for, and let's see how far we can get with that. So the first thing to begin with is the simplest, in some sense technically, question of incompressible, inviscid fluid with a free surface. So it's for the typical example is water in a pond, and I want to talk about a disturbance created on this free surface. So disturbance created on the free surface, and what happens? What is something now spreads out in the form of ripples. So so ripples are wave, and we are going to see how to find the velocity of spreading of that wave. So that's the first problem to do. So the point is, let's look at the conditions that I have put. Inviscid fluid, so viscosity off for the time being. Incompressible, so incompressible means divergence rho is constant everywhere, divergence V equal to 0, rho equal to constant. So divergence V equal to 0. Now is this question of disturbance that is created. So in the event of no disturbance at all, I have a flat surface. Here is Z equal to Z0, and there is water below, and here is the bed, let's say at Z equal to minus H. That's where I have the bed of the pond. So this is the bed, and here is atmosphere. And the first assumption that I make about this disturbance that I have created is that it spreads. So the disturbance spreads with a small amplitude. So disturbance spreads with a small amplitude. So obviously you disturb some particles of the at the surface over here. You disturb the fluid particles in some region like this, and then it sort of spreads. The movement of these affect the next batch of particles. The movement of these affects the next batch, and so on and so forth. So there is that's the spreading of the disturbance, and what we'll see is that gravity will be the important effect. So all right. So you do expect that, I mean, the static condition gives me a flat with a certain pressure distribution given by gravity, and so I'm perturbing about it, and gravity, as this particle as sort of go up, gravity tries to bring it down once again, and so on and so forth. There would be another important issue over here, which I'm going to ignore. That is the I'm going to ignore important player, that is surface tension. I'll talk about another example with surface tension a little later, and then maybe you can bring surface tension in this problem and see what kind of effect surface tension may have. But for this present discussion, I'm going to leave out effects of surface tension. So all right, now what the important issue is that I'm assuming that it is a small amplitude business. So small amplitude, now what's the relevant equation? Relevant equation, no viscosity, so incompressible. So my good old Euler equation with V dot equal to minus gradient of P over rho plus G, let's say minus G Z unit vector. So unit vector Z acts upwards. So del V del T equal to this. Now what's the significance of saying that, the whole idea of saying that I have made a small amplitude disturbance is to make life easy for me. So how do I make life easy? So let's say the amplitude of particle motion because of this fluid particle motion amplitude is, let's say, some A. So the amplitude of particle motion is A. So the time, I mean, there is going to be restoring business as you can imagine. There is going to be movement which is going to be, I mean, as they are disturbed, they'll be brought back by the fact that gravity pulls them back, and then because of the incompressibility, the next bit gets affected, and then gravity has to, and incompressibility and gravity lead to the propagation of this. And propagation meaning that there is going to be this disturb, restored, shoot past, go back, and so oscillations over there. And time of oscillation, that oscillation time is, let's say, some tau. A typical velocity then is equal to, is like A divided by tau. So that's my, this tau, which is oscillation time, could be written as A over V. So all right, given that, let me make some estimates over here. So del V del T. So del V del T, this is to be estimated, my estimate for this is going to be V over tau. So V over tau is writable as, because of that relation over there, this is like V square over A. So that's the estimate for this chap over here. Now what about this? I have to estimate, make an estimate of V dot grad over grad time of operating on V. So I need to know over what scale does V change. So here is a wave propagating on this disturbance is propagating, and it propagates obviously with some wavelength lambda. So V changes, which means that V changes in a distance of order lambda. So when I estimate this chap, it's going to be V square over lambda. So so this fellow is estimated as V square over A, and this chap is estimated as V square over lambda. So if I am in a regime where lambda is much greater than A, that is the wavelength is much higher, much bigger than the amplitude of the particle motion, then the V square over lambda this term would be negligible. So drop nonlinear terms, problematic things anyway, so any excuse to get rid of them. And this seems like a very reasonable picture. If I look at these ripples, the ripple wavelengths are quite big and the amplitude of motion is. So what you see in real life is not very different. So that immediately allows me to write del V del T equal to minus gradient P over rho minus G Z prime. So the dynamics that I'm going to worry about becomes this simple statement over here, that del V del T is minus GZ. So now the question is, what can you tell me about the vorticity business for this flow? A flow governed by this, whether do you expect it to be rotational or irrotational? Irrotational. Irrotational, why? Because all that I need to do is take a curl of this equation, and del del T of curl of V is equal to 0. So curl of V is independent of time, and initially when I start out, it is 0 vorticity, the static situation with 0 vorticity, and therefore I can go happily use irrotational approximation. So this one, so omega equal to constant in time, and omega equal to 0, T equal to 0, and remains so forever. So very good. So that makes our day, that I have a bona fide example of a potential flow. So great. I mean, I can now write down that V is equal to gradient of phi. So potential flow, V equal to grad phi. And now what is Bernoulli when V is equal to grad phi? What's Bernoulli going to be? Tell me. P over rho plus half V square plus GZ equal to constant, right? So that's the business, plus I have not written a term, plus del phi del T. So del phi del T plus P over rho plus half V square plus GZ, that's going to be a constant which depends only on time, a constant in space. So it's a function of time, and I can always choose that function of time such that I can absorb it in this phi and call this chap 0. So very good. So that's the constant. But now, from what I have said over here, can I drop some term over there? In this Bernoulli thing over here, can I drop something? V square. Out goes V square. If I'm not going to have a V square over here, then I don't want a V square over there. After all, it came from here. So out goes v square, and I have a rather nice situation, plus gz plus del phi del t is equal to constant. So now, at t equal to 0, you have this flat business where it is some t equal to 0, you have, let's say, some p0, and p0 over rho plus gz0 equal to constant. So that defines z equal to z0 is your initial undisturbed surface, and so I make a perturbation now around that situation which I had. So this undisturbed static situation, and I'm going to make a perturbation around it. So very good. The perturbation is going to say that z, the surface, has moved from z0 to some z0 plus xi, and this xi is small. So this is the surface. The surface is now given by z0 plus, so you have this displacement over here. This displacement is my xi. Very good. So I have a delta p over rho plus g xi plus del phi del t is equal to 0. So that's on the surface. So I change the surface to some z0 plus xi, and the pressure fluctuates to, let's say, p0 plus delta p, and then it is g xi plus del phi del t equal to 0. So that's my advantage of setting the constant always equal to 0. But now delta p is 0, because everywhere on the surface over here it is the same atmospheric pressure. It was atmospheric pressure over here, it's atmospheric pressure over here. So that doesn't change. So I have this on the surface, this fluctuation in pressure goes to 0. So on the surface you have this situation on the surface. You have del phi del t is equal to minus g xi. Let me take a derivative. Then del 2 phi del t square is minus g del xi del t. Xi is the vertical movement. So del xi del t is Vz, which is del phi del z. So this is equal to minus g Vz, which is equal to minus g del phi del z. So on the surface I have the condition that del 2 phi del t square is equal to minus g del phi. So on the surface I know what's going on. Good. Now I have to find this phi. So now is the question of finding phi. So what do I use to, what is the equation that phi satisfies? I have to find phi. So what's the equation for phi? Del square phi equal to 0. Now, so phi is a function, let's take this as the x direction, that's along the, it's going to be a function of x, y, z. I'll drop the y. I mean, just talk about propagation in this direction makes life simple. In reality, I should have talked about propagating out in cylindrical form, but that just without makes the maths cumbersome without making the physics any more any different. So this is f of xz. So I'm just suppressing the y and talking only about propagation of the wave in the x direction. Now, if I have a propagating, I'm looking for a solution where it is a propagating wave in x direction, then there has to be this propagating wave in x direction must have a dependence which is cos kx minus omega t. K is the wave number and omega is the frequency. So it is cos of kx minus omega t, and then multiplied by f of z. That is the potential that I'm after. So the structure of the potential function that I'm after is fz cos kx minus omega t. If I were finicky, I would write k dot two-dimensional vector r minus omega t, and but that's all right. So now I'm in the business of solving this. So what is with this del square phi? Huh? Pardon? What? See, f of z has nothing to do with the wave propagation. So a separation of variables in this case is the absolutely different kind of physics in the two different directions, and therefore my boundary conditions are only on the z part. So I can happily look for a solution which has a separation of variables. So the physics is very different in this direction where I have to satisfy boundary conditions, and in this direction where it is just a wave propagating, and so quite all right. So fz cosine kx minus omega t del square phi equal to 0 is del 2 phi del x square plus del 2 phi del z square. Otherwise, it would have been the two-dimensional Laplacian plus this. So that's it. Now, I have made a statement about phi. So this is going to be minus f del 2 phi del x square. So f not affected by it. And this is going to be minus k square cosine kx minus omega t plus d2f dz square and cosine kx minus omega t. So d2f dz square minus k square f is equal to 0. So f satisfies the equation d2f dz square minus k square equal to 0. And all right, now I'll come back to use that picture one more time. Good. So I have to solve this. What is the answer? Straightforward. A cosine hyperbolic kz plus b sine hyperbolic kz. What's the boundary condition? So boundary condition at the lower plate, what's going to be the boundary condition? boundary condition on phi at this lower plane at the boundary condition on velocity at the lower plate, and hence the boundary condition on the phi in the on the lower plate. Vz is 0. So therefore del phi del z is 0. Therefore df dz is 0. All right. So df dz 0 is equal to df dz at z equal to minus h is equal to k a minus sine hyperbolic kh plus k b cos hyperbolic kh. Good. So that so is b is equal to a tan hyperbolic kh. So now I have a relation between. So where is the other boundary condition? The other boundary condition is over here. On the surface, del 2 phi del t square is minus g del phi del z. Where is the surface? The surface is at z equal to z0 plus h. That is the surface. But displacements are surfaces at z equal to z0 plus xi. But this is already an equation which involves small quantities. So therefore, when I want to enforce this boundary condition, I can set xi equal to 0 at to begin with, and therefore this equation, which is on the surface, being an equation in the small perturbations themselves, has to be satisfied to the first order in smallness, to first order in smallness at the flat surface z equal to z0, which by this reckoning, so at z, which is essentially z equal to z0 equal to 0, the flat surface. So the token by which I have put a minus h here. So z equal to 0, that's the flat surface where this chap has to be satisfied. And so that is going to give me del 2 phi del t square. So del 2 phi del t square comes from over here. So it is minus omega square and minus omega square and f of 0. So minus omega square times f of 0 equals minus g del phi del z. So del phi del z, so that brings in this f prime of, so there is a, let me not forget, there is a kx minus omega t over here. Then there is a del phi del z, which is df dz, and df dz is this character over here. I have to take a derivative, and then k comes out, and then it is, this one is a sine hyperbolic, and this one is a cos hyperbolic. So this is going to be minus gk times b and cosine kx minus omega t. So these factors cancel out. F0 is a, so this part is a. So you have the result that omega square is equal to gk times b over a, but b over a is tan hyperbolic kh, so gk tan hyperbolic kh. So omega square is equal to gk tan hyperbolic kh, and you now have two. So this is the dispersion relation, and this dispersion relation, if h is, if you have a, so you can see that it's a non-trivial, and omega square is equal to gh. So the surface deformations in a thin layer of fluid propagate as omega square equal to gh, whereas if it is h large, this example where I drew a pond rather than a thin layer, there the tan hyperbolic kh is going to saturate to unity, and you are going to get the dispersion that omega square equal to gk. The velocity over here is omega square is this, and the velocity is g times h, whereas the velocity in this case over here, v square is equal to 2 pi, and then it is g times lambda. So the velocity depends on the wavelength of the, so that's the non-trivial dispersion when you have, when you see these ripples propagate on water. It is a standard dispersion with v square equal to gh, the square root of gh, the thin layer waves which have this, which may have been familiar to you. So that's the ripples that you see, the two different kind of ripples in a shallow bed, in a shallow water body and a deep water body. And let me make a comment about this particular v square equal to gh, which you may want to at least, go home and look at. If you look in your kitchen sink, you have this faucet draining water, discharging water at a high speed, so high speed flow over here. If you look at the base of your kitchen sink, the water impinges over there and flows out in a circular pattern, and then after it has gone a certain distance, let's say some capital R, it jumps up. So if you haven't seen it, it's, you can go and check it for yourself at home, that, that there is this phenomenon that the water level, it flows out fast, and then after some point there is a jump, and thereafter this fast flow becomes a somewhat slower flow and a much choppier flow. It's sort of, so you ask the question, what happened? What is this boundary? And what is this boundary is, amazingly enough, it is the boundary where the, now as this water flows along the sink bed, there is viscosity which sort of slows the water down. Over here, it is extremely fast when it's starting out, but then it gradually slows down a bit. And when it is starting out, the velocity of water is greater than square root of gh. And when it reaches this boundary, then the velocity, what is the boundary? So it slows down because of viscous action, and then when it reaches the boundary, it is v water is just the square root of gh, that is the wave velocity. And that's where the boundary happens. And what is this boundary then? So think of So you are looking at, now, what's the job of a wave? The job of a wave is to transmit information from one part of the fluid to another. That's what we started talking about. I drop a stone over here, cause some disturbance, and this wave carries the information about that disturbance from one part of the fluid to another. So its the role is to carry information about the disturbance. So very good. So now here is this fast moving fluid. If there is some disturbance going on in this part, then that disturbance has to travel through this speed with the speed square root of gh and spread to other parts of the fluid. But the fluid, when moving with a velocity which is greater than, is going to drive away this wave that is coming in. So for the, after all, these are velocities which are obtained relative to the fluid at rest. So for an observer like you standing outside and watching this sink with the water flowing through, the effective wave velocity is that minus that of the water, and the wave is transmitted, wave is, if it's trying to come in, it is going to be driven out. So no information can pass from up to this edge over here. No information can pass from the outside to the inside. So no information. Now, what's the information that you should have obtained? The information that you should have obtained is that, as this is moving around, the lower levels are getting slowed down. So it is the part of the fluid which is attached to the and very close to the bed that has slowed down. But that information can't. That information has to travel via the water wave, and the water waves are driven out of your system. So that can't. So you have this top fluid, top layer, also sort of rushing forward, and then finding that, the lower level has slowed, and then when it hits the boundary, it gets the information and has to jump up to accommodate for the slower moving levels below. So that's the qualitative picture of this jump. And if you want to see this verified, you can look at the word. The phenomenon is hydraulic jump. And if you look on the net, you will find pictures of an experiment which clearly demonstrates that the boundary is the condition given by this. That is the boundary of the phenomenon that you see in your sink. And they do this, the standard experiment which you do with sound waves, the Mach number, rather than opening up this cone, Cherenkov kind of cone. That is what the experiment does, and verifies that the boundary indeed is this condition over here. So the water wave has, and obviously whenever it is one-way traffic of information, there is temptation to relate it to astrophysical objects. So whether that's kosher or not is another matter. But then, I mean, one can feel happy that maybe you are seeing an astrophysical object in the kitchen sink. So, yeah. Huh. Sure, absolutely. And you can control it by adjusting the speed of the flow. So, all right, phenomenon number one. Yeah, sure. Yeah.
Water waves are sometimes at that point, sometimes not there. So del U and del V is changing in a discontinuous fashion.
fact that as this seabed, when you come close to the, why do you have this wave which is traveling inside dump so much energy when it comes to the edge of the ocean? And it is the whole business of the bed sort of rising over here and giving a much shallower depth in this. And so you have these waves which are coming with a much higher speed, and then over here you are supposed to have slow down, and that adjustment essentially leads to some energy transmission on the speeding up of or rather depositing energy on the bay. So there are some calculations. There are, calculations with question of starting out with a disturbance which happens in the middle and getting in that. Somewhat more complicated, and therefore, but at the end of the day, there is a result which is very similar to this GH, and temptation to try and explain some of the features of what the devastation by looking at this change in bed. Yeah. Paints, burger paints, or what have you, right? I mean, things sort of which look like this, red over here, generally the favored color. It is, what have you done? You have taken a brush, dipped it in this red Asian paint or what have you, and sort of used the brush to do this. And then you have done, so painted this part of it. So you have put some paint, and the paint begins to trickle down. It does not trickle down as the surface dividing the paint and non-paint, just the surface coming down. It comes down in the form of fingers. Question is, what caused these fingers, and how big are the fingers? Can I give, does hydrodynamics give you the answer? So, so what happened? So what happens is that there is air over here and there is paint over here, which you change to heavy fluid over here and a light fluid. So say some ρ2 and a light fluid. So that's a top-heavy situation which gravity doesn't like. So fine, so gravity doesn't like it, and it would want the heavy fluid to come down. But coming down is not so easy, because the fluid is incompressible. So you don't play games with incompressible fluids. So it's not possible that this heavy fluid would just come down. So it starts out by making inroads. So it's sort of a bit of the light fluid pushing in over here, and a heavy fluid coming down, and the initial thing would be that the flat surface would become sort of wavy. So flat surface becomes wavy, but surface tension doesn't like it. Surface tension is a force which origin is intermolecular forces, which says that for liquid, the minimum, a given mass of liquid, minimum surface area is preferred. So so it costs energy to increase the area. So surface tension would say that the minimum area should be minimum surface area should be the proper form. And if that is so, then all liquids should come as spherical droplets. Doesn't happen. Why not? Because there is gravity always trying to be nasty. So you don't see these perfect fluids, but you do see it sometimes. If you watch, if gravity is eliminated. When is gravity eliminated? If I look at these dewdrops on leaves and they detach themselves from the leaves, you will see they detach by forming a sort of elongated structure like this, and then when they fall, they become a perfect sphere. Because in free fall, gravity is gone, surface tension the only actor, and then it reduces, then it says minimize the surface area, and you have these perfect spherical drops which fall after a while. So you can, and then the very high surface tension liquid like mercury, take small drops, that is, break your clinical thermometer and see the mercury comes out in small drops. Small drops, gravity is not very effective, and those mercury drops that come out are perfectly spherical. So surface tension works, also works in Tintin comics, where Captain Haddock's whiskey comes out in outer space in perfect globules. So so that's surface tension says this flat was all right. Change it to a wavy surface, it's going to cost you energy. And the more wavy you make it, the more excess energy, the more the costlier it is going to be for you. So there has to be a compromise. The point would be that when this gets this surface gets deformed over here, you cannot have a very wiggly. This is not allowed. So it has to be, there has to be a wavelength which has to be greater than a critical wavelength. Otherwise, the gravity effect will not be seen. And that, we'll find the critical wavelength in a minute. But you have seen this critical wavelength business very often. If I take this bottle, open and invert it, the water will come rushing out. But if I take a homeopathic medicine bottle and invert it, nothing happens. The hole is much too narrow to have this heavy fluid come out of it. Surface tension wouldn't allow that to happen. So you can look at it in another way. Surface tension actually stabilizes a top-heavy situation. So now, given this, all these phenomena, what is how can I estimate the critical wavelength? Well, let me calculate. So here is the surface deformation that's formed, and so this is Z equal to A cosine kx. That's my surface over here. So I have to estimate how much gravitational energy do I have in this bit over here. So how much gravitational energy? This amount is, so it is rho times g times dz prime times z prime times dx, if this length is dx over here, times 1. 1 is the extension perpendicular to the board. So here is the volume, dx times 1 times dz prime, and here is the energy of that volume, which is this. So you integrate this from 0 to z. So you integrate that from 0 to z, and the answer is rho g dx, sorry, z square divided by 2. And then you have to integrate over, let's say, one wavelength. So over one wavelength, it is going to be over 1 lambda. I put z equal to a square cos square kx, and then it is rho g a square cos square kx over 1 wavelength is going to be half. So that is rho g times a square divided by 4. So that's the amount of gravitational, so how much gravitational. So the excess area is this half into dz dx whole square, and that's your so half dz dx. So the excess area is that. So excess surface tension energy is, if the surface tension is S, then over one wavelength, you carry out this S over 2. dz dx gets you k square a square cos square kx integrated over 1 to this. And so over a wavelength, so it is S times a square into k square by 4. So this is, you have to, surface tension for a wave number k would demand this amount of energy. So k, if k is very big, gravity gives you a fixed amount of energy. So the maximum k that you can accommodate, the k max is equal to, when these are equal, and then it is g delta rho divided by S. So the lambda min, lambda critical is 2 pi over k max, so that's 2 pi S over. So so that's the lambda critical that you get, and unless you have lambda greater than lambda critical, surface tension is not going to give you the. So this is, if you work between water and air, you will find that this lambda c is of the order of 1 centimeter, and that's not a particularly bad estimate. But on the other hand, this is the beginning. The actual phenomenon is far more complicated, because this is just the initial surface tension alone. If you see these patterns, computer simulations or real life patterns that form, they are more complicated. It is not the different, there is a distribution of these wavelengths, as you can sort of see in this rough picture. Also the edges are not very smooth, so there is the other kind of instability that viscosity can induce. Maybe, I mean, in the tutorial we can talk about it, the fingering variety. And so there are complications in real life, but you can look at this in two different ways, that surface tension can stabilize heavy fluid above light fluid under in certain containers, like the homeopathic bottle. And all right, I mean, if it is an instability issue, then patterns would be formed with a very definite distribution of wave numbers. So and this raises the final issue over here, which I'll have to tackle, that it's an instability. and instability. This is just a statement that there is an energy disbalance, and so you get but what tells you that it is a real instability, in the sense that if I take this flat interface and give it a wavy perturbation of this kind, is the perturbation going to grow with time, or is the perturbation going to die down with time? So the real calculation would have to be that I have to give the interface a wavy perturbation and see, as time goes on, is that perturbation going to decay, or is that going to grow? If the perturbation grows, then the flat interface is unstable. If not, there's that. So there is this question actually of hydrodynamic stability that would have to be. The good thing is that the answer that you get is still, it will tell you that if lambda is smaller than lambda critical, then it will grow, but the expression for lambda critical would be off in a real calculation, in the dynamic calculation, from what you have over here by a factor of square root of 3. If you see the real calculation, the factor of 3 would be you would say that you would rather settle for a factor of 3. So root 3. So it's quite nasty. The phenomenon is called a Rayleigh-Taylor instability. And actual working out is complicated by the fact that this matching at the boundary condition with the surface tension in is a bit of a problem. Just a technical, requires a bit of manipulation. All right, so this is one. Now let's come back to another problem, which is also of the instability variety, which is that how advantageous would it be for you right now to be in Ooty rather than over here? So that's the next question that I want to address. So what's the issue? The issue is that what you saw in the last 3 days at various points, Sanjib had it, Jayanta had it, that questions of equilibrium distribution. And at one point, the issue was that if I have a column of gas, then there is a distribution which would mean that there are lesser number of particles, that's a lower density as you go up, which is very clearly seen by the result that Sanjib had yesterday from Fokker-Planck, which gave you equilibrium density which went like E over the potential energy times divided by kT. So that's for this case like sort of mgz by kT. So you have a decrease as the height goes on, the density decreases, and that's a valid equilibrium distribution. But the point is that you don't live, I mean, why would you rather live in Ooty at this point? Because the temperature is not constant. I mean, that is, as I change with height, the temperature decreases. So that's the whole idea of being in hill stations. So, but temperature decreases means that the density increases. Yeah. So now the point is that this equilibrium distribution, which is isothermal in nature by its very construction, says that the density does decrease as you go up. Very good. But life tells you that Ooty is better than Bangalore, and therefore temperature, there is a question of the temperature decreasing as you go up, and should I still have a stable atmosphere? So that's the issue. So I have a, how would I look at the question of a stable atmosphere in that case. So what would I do? I have this issue that density or pressure decreases as I go up. I have the temperature which also decreases, and I need a condition for the stability. How do I get a condition for the stability? This is once again doing qualitatively what all stability analysis in maths would, the maths of the stability analysis would do. That here in this, I consider a volume, take a mass of fluid, and consider the volume of that, a given mass, let's say unit mass. So V, which over here, I'm going to use the variable rho, the density, the volume, let's say the pressure, what have you. So talk about the V as a function of this pressure over here, and the entropy. So I'll use the volume of a unit mass. It has to depend on two independent thermodynamic quantities. So one of them, let's say, is the entropy. The other is the pressure. Out over here, it will have a certain pressure corresponding. So let's say this is at a distance xi from here, not too much, a small distance xi above it, and the corresponding volume is different because it is a function of the corresponding entropy and pressure at that point. So it is V of P prime and S prime. So what is stability? The stability would mean that if I were to move this up over here adiabatically, so it does not lose its heat content, and then look at this over here, it has Vp prime but the same S, then this Vp prime over this S over here has to be stable, means that if I take it over there, it has to drop down. So if it will drop down if it is at a higher density. So if its density is going to be higher, it will have to drop down. So stability implies that Vp prime S is smaller than Vp prime S prime. So this is what I have. So the stability condition is that V of P prime S prime is greater than Vp prime S, and this I'll Taylor expand as V of P prime S plus S prime minus S into del V del S at constant P and plus higher order terms, and so this is minus this. So this minus this has to be greater than 0. So this is minus V of P prime S greater than 0. So this is entropy. So it is del V del S P ds. So S prime minus S is ds dz. Z is the height over here times the displacement xi. That has to be greater than 0. But this over here, del V del T, this can be written as del V del T P times del T del SP, and this is the expansion coefficient. This is expansion coefficient which is positive, and this is the inverse of the specific heat, give or take a temperature. So this is 1 over Cp, rather T over Cp, and so that is greater than 0. So this is safe, this is greater than 0. So I must have for this that ds dz so ds dz has to be greater than 0. So it is del s, so s as a function of p and t, del s del p at t times dp dz plus del s del t p, and that is dt dz is greater than 0. So this is my del s del p is minus minus del v del tp. So that is minus del v del tp, and this is dp dz over here. So let's see what what games one can play with this. If I have a ideal gas that one is talking about, then this is going to be del v del t p. So it is pv equal to r t that one is talking about. So del v del t at constant p is going to be nr divided by p. So you are looking at this term over here, which is minus, so this is equal to minus n gas constant d of log p divided by dz. The pressure is determined by the density distribution. The density distribution, which you know is like, P, the density distribution is like rho e to the power minus m gz, which gives you log rho or log p, which would go like minus mgz. So this is just dz, and so you have minus. So this essentially is equal to minus with a minus gives you a plus m times n times g times r. So this is m times g r, and out over here this is specific heat. So dt dz has to be greater than minus, so this is Cp over here, and this is mngr divided by, so there is T over here, that's T divided by T, that's a Cp, so that's Cp over here. Hopefully I have got, more or less. So let's see. I can get the number density in terms of T, so equal mass, something or other. That's the, so dt dz, the important thing is the sign over here. So it's the sign over here, which means that there is a maximum cooling. There is a maximum cooling which you can sustain. So there is a maximum cooling which you can sustain. The atmosphere would be stable so the atmosphere would be the maximum temperature gradient that it can sustain is m times n times g times RT over Cp. That's the sort of T mean over here. And one needs to look at the algebra a bit closely to see if this can be further simplified. But that's, I mean, the 1 over Cp is certainly right, and the G on the top is certainly correct. So the maximum temperature gradient, or rather the adverse temperature gradient, that you can sustain for a stable atmosphere has a certain critical value. And if you put in the corresponding numbers for air and so on and so forth, then you would find that this is roughly 10 degrees for 1 kilometer. So 10 degrees centigrade for 1 kilometer, that's about that's the maximum that you can sustain. So if you were to be in Ooty right now, the coolest possibility is something like 12 or 13 degrees centigrade, which certainly is desirable. But anything but you can't have it arbitrarily low, and there is a limit beyond which the atmosphere would become unstable. So that's the starting off point for talking about another instability. So the whole idea is that right now one is trying to go into the issue of turbulence. I'm looking at instabilities, that things you have a particular nice and simple fluid flow, and that may not be the state of affairs. So things can become complicated. Fluid flow does have, being a nonlinear differential equation, the happy situation that given, for example, when we were talking about, I mean, Fokker-Planck and so on, you have initial condition and boundary condition and unique answers. But this is you are faced with a nonlinear differential equation, and those uniqueness theorems don't follow anymore. So you have a variety of solutions which you can have, and therefore you have to look at stabilities of these solutions. So the one particular kind of stability which is reasonably easy to describe physically and model mathematically is the question of convective instability. Again, something which you, fluid layer of height d, which with T1 greater than T2. Something once again which you see very often. You see it on pavements. Say if it were to rain right now and stop, and if you were to look at the pavements, you would find that the dust has settled on the pavement in some pattern which roughly looks like this. It's not, it's some kind of broken hexagons. You see those broken hexagons again if you were to boil off water containing spices in a saucepan, and what is left behind is a trace of the fluid movement when it was there before evaporating, and that fluid movement once again leaves a pattern which is more or less like broken hexagons. So what is going on is that there is this, everywhere in all such phenomena, the fluid motion is of convective variety. That is, the hotter fluid, you heat it from here, heated below, the fluid rises, and the hot fluid rises, the cold fluid falls, and you have this pattern, which in the simplest drawing, one always draws it as being sort of a cylindrical geometry. That's easiest to draw. But when the pattern really forms, it is not a cylindrical geometry. Preferentially, it's always a hexagonal geometry. Why? Nobody knows. So once again, everyday observation for which there is no quantitative answer. So fluid mechanics has this great advantage that if you just look around, you will find things for which calculations can't be done. For example, in the hydraulic jump problem, if I were to ask you exactly at what radius in that sink did the jump take place, there is no answer for that. So all over the place you run into problems which look doable, but which are not. But then there is this one which I'm talking about, so convection. But the point is, will convection occur? Is it guaranteed that I take two plates with a distance d between them, heat the bottom plate? Am I sure that the top plate, that there is going to be convection going on? Well, suppose it, how do I, so back to the argument that we went through a minute ago. I'll take a hot parcel of fluid from here. So this is the hot fluid from here, and I'm going to take it over here. So here is, I'm going to move this hot fluid up. So now over here, its neighboring business is quite cold. So this is a cold environment, and this hot chap has come up over here. And if it has come up over here and still remains hotter than its environment, then it's certainly going to go further up. But if in the process of coming up, it has cooled, then of course, I mean, this is not going to, there is going to be no convection in your problem. So why should it lose its heat? Question is, there is thermal conductivity. Fact that I have gone on talking about conservation laws of entropy, situations where there is no exchange of heat between one part of the fluid and another. That obviously has to be relaxed. And there is this thing called thermal conductivity, which probably the last time that you saw was in your high school days. And, but it is something which is, unless probably if you are in RRI where Abhishek makes you look at thermal conductivity, but then that's for a few. And so thermal conductivity, which tells you that if there is a temperature gradient, then there is going to be amount of heat flowing from hot temperature to a lower temperature is going to be this lambda times dt dx per unit area. And so this thermal conductivity will say, aha, this hot fluid is going to lose its heat. So by the time it has come up over here, it's no longer hotter than the environment, and no question of it's going further up. That's the end of the story. So it's not going to be unstable. So I need to estimate whether it has lost its heat or not. So how do I do that? I need to first, then I need to know that's the rate at which heat is being lost, lambda times dt dx. I need to know what time did it take for it to go up. So what is the time? So let's say the time tau, which is the time to, if this distance over here is L, then it is the time to go up is tau equal to L over V. Now, that of course assumes that it is going up with a uniform velocity. But why should it go up with a uniform velocity? Well, that's what you have been hearing the last 3 days. Well, you have been hearing it goes down with a uniform velocity. I'll just make it stand on its head and say going up with uniform velocity, because now the buoyancy force is bigger. So it's buoyancy which is driving it, therefore it's going up. If it goes in the upward direction, Stokes' law will resist it. And so you can say that eta times r times v is roughly equal to the 4/3 pi r cubed, the volume of this thing, times delta rho times g. So that's so delta rho is alpha. So 4/3 pi r cubed. Who cares about 4/3 pi and so on? Don't care about the 6 pi either. It's r cubed rho times expansion coefficient times delta t times g. So I know what the v is. V is alpha delta t g divided by eta by rho, which is nu, and r1 has cancelled out, it is r square. So that's the so that's the velocity. So this time is L divided by V, so it is going to be L times nu divided by alpha delta t g times r squared. So this is the time. Now, what's the time for heat to diffuse? Diffusion equation you have been seeing every day. So once again, I mean, temperature will follow a diffusion equation, and that diffusion equation is going to be T dot is equal to the thermal conductivity divided by rho times Cp times del square T. This is the heat diffusion coefficient, call it kappa or what have you. So it is the heat diffusion coefficient times kappa. So all right, T dot is del square T. So what's the characteristic time which is involved in this heat diffusion? So diffusion time is going to be, so this is d square divided by kappa. So d, so that's the length scale divided by kappa. So that's the, so left the length scale that I have taken is L. So L square over kappa is the diffusion time. So there is a diffusion time, tau diffusion is of the order of L square divided by kappa. Now what? Now you don't want the heat to diffuse. If you want it to be unstable, unstable means that heat cannot diffuse fast. That is, if the heat were to diffuse fast, it would lose its heat and cannot go up. So only if it maintains its heat content can it more or less, it would still be in a colder environment and would be going further up. So instability would have to mean that tau is greater than tau diffusion, and tau greater than, now there are these length scales floating around, L, R square, L square. Now what are they going to be? There is just one length scale in the problem, which is D. So this L has to be some number times D, the R has to be some number times D, and therefore let me just put D everywhere, and it is D nu alpha delta T G D square has to be greater. So unstable, if it's the other way around, diffusion time is big, so you don't diffuse, and that's by d square over kappa. So put things together, it is 1 less than alpha delta t g d cubed divided by nu times kappa. So in the problem you have a dimensionless number called the Rayleigh number, generally written as Ra, and what you find is that over here I have said that this argument with dropping all numbers in the world, that is numbers like 1, 2, pi, e, and things like that, it is Ra greater than. What it means is it is greater, it has to be greater than some critical value before convection can take place. So there is a critical number for this Rayleigh before, otherwise this instability cannot take place, and the solution with no movement of fluid, with only conducting heat conduction from the bottom plate to the top plate, would be a stable solution of the hydrodynamic equations. Only if Rayleigh number is greater than a critical value would convective motion start, and that's the something, the critical Rayleigh number for realistic systems. This critical value is 1708. And that's something that you can verify in labs and in numerical simulations to better than far better than 1%. So one part of, obviously this part of hydro has no difficulties in making predictions, and there you are. So, well, we'll use the tutorial hour to tell you how the maths goes. The maths is easy in this case. The maths has to, exactly the physics that was described has to go with the maths. The procedure is called a linear stability analysis. Quite extremely straightforward business, really, once you get the hang of it. And so that's that. And the way it goes is that, all right, at this particular Rayleigh number, it becomes a steady convecting pattern. Increase the Rayleigh number a little more, and then you find that these rolls or hexagons, if you want to be realistic, they start wiggling. So you have the axis of these rolls start undulating. With a given period, if in the beginning, raise the Rayleigh number still higher, the undulations become not with a single frequency, but with a couple of incommensurate frequencies. Raise it still further, it eventually becomes a bit of a mess, and that mess is what is called turbulence. So here is a typical system where if I control the Rayleigh number, a system would make a transition from a well-defined state where no motion is taking place to a convective state, to a more complicated and then to turbulence. Similarly, the pipe flow, which I talked about last evening, that if I increase the Reynolds number in the pipe flow, the parabolic profile gets changed as there is time dependence in the flow, which sets in more complicated, first with a periodicity, then with a more complicated quasi-periodicity, and then again goes haywire into a more So that's where one is headed, and this today at least, I mean, this was all essentially qualitative physics of what goes on. So anything that while at it, I mean, this is certainly easy to go over because no maths to worry about. Yeah. Huh. 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 All right. the point is that the thing is that it is a question, see over there, the instability is driven actually the above a lambda c, which has a couple of things in it. One is the delta rho between, and the other is the question of surface tension between the two. So if you have a situation where the delta rho's are not too different, I mean, you see it very clearly when it is real heavy fluid on top, and also with a surface tension which is far. So water and air, you see it almost very clearly. But if it is near enough density, you and also near enough densities almost always also reduce the surface tension very strongly. So if you have a very low surface tension, that's going to be, you are not really going to see it. But have a clear-cut largish surface tension and big density difference, it's sure to show up. Also, I mean, it's a question of this critical wavelength. I mean, if the wavelength is, I mean, if the wavelength that you can, the smaller you make the wavelength, the more, the greater is the possibility of seeing it in real life. And of course, in the direction of gravity, I mean, in vertical, it has to be vertical columns of, yeah. And so the system size versus the wavelength, and so narrow system size generally, yeah, stabilizes